Hello, everybody. Welcome to this year's Pacific Northwest Climate Week. Thank you for joining us. My name is John Meyer. I'm the Senior Director for Marketing and Communications at the University of Washington College of the Environment. I'm honored today to introduce this session's speaker, Dr. Cecilia Bitz, who holds the Jerome M. Paros Endowed Chair in Atmospheric and Climate Hazard Research and is one of the world's leading experts in Arctic climate change. She's a professor here at UW and is interested not only in our present and future climates, but also climates of the past. She focuses her research on improving our prediction of Arctic sea ice and the interactions between the air, sea, and ice that control large-scale climate. Sea ice and climate change will be the focus of Professor Bitz's talk today. Please be thinking about questions you may have to ask, as there will be time for some Q&A at the end of the talk. You can drop your questions into the chat or comment section at any time. Okay, Dr. Bitz, the floor is yours.
Thank you very much for joining us today. I'm really excited to talk to you about a topic that I love. I think we are all fascinated by snow and ice because of its beauty and its influence on our climate. It's also really ephemeral and it has changed dramatically. I'm going to kind of cover 4 points in my talk. First, how sea ice is a foundation to Arctic communities and influences the way of life of Indigenous people. It is also a protector of these villages. It regulates their temperature, it maintains permafrost, and suppresses ocean surface waves that inhibit coastal erosion. And sea ice is the air conditioner of the whole planet, so it benefits all of us. Its loss amplifies global warming, so it's a serious concern. And finally, I want to wrap up with, can we still save it with public policy? And are there any adaptation options? I wanted to tell you a little bit more about who I am. I know John already did, but I think of myself as a climate scientist, but my specialization is in sea ice and climate modeling. I still have been to the Arctic a few times. I'm very lucky to have had the benefit of seeing the thing that I model, which has always changed my thinking really dramatically. But I think of myself as a physicist, and I really like to think about the details and the microphysics and how it influences kind of the macro climate scale. I was in the Arctic in January this year, and it was cold. I'm actually wearing two down coats. That's why I look pretty well insulated there. But I hope to talk to you a bit more about all of the other pictures here as the talk progresses. I'm an alum of University of Washington, professor now, but I was really lucky to study here because University of Washington's close proximity to the Arctic, and because Seattle is a good port. We have historically had icebreakers parked in Seattle. There's one stationed here now, the Polar Sea, and it's the largest, the heaviest icebreaker of the fleet. But our Polar Science Center here at University of Washington is run logistics, and we have field programs almost every year. And this looks like field camps sometimes, or research from a ship, or people actually on the ground. And I've been lucky enough to join a number of times. As I said earlier, sea ice cools the planet. It does this because it's so reflective compared to the ocean, which is highly absorbing of sunlight, but also because it's a really good insulator. So it prevents or reduces the heat released from the ocean to the atmosphere. So it acts like a coat and keeps the ocean's heat in the ocean. Um, we have lots of great ways to image sea ice. Here's a photograph taken by a person on the ice, and I want to differentiate it from icebergs. It is frozen seawater. It's very expansive compared to land ice. And land ice, when it breaks off the shelves or the terminus of the glaciers, can look like these giant icebergs embedded in the sea ice. They're really much thicker. The sea ice itself is about as deep as a person is tall right now. It can be thicker, and it has historically been thicker. You might think of it sort of as tall as a house. Uh, this is a video that I hope to get us all situated. See where, of course, the Arctic is at the top of the world. Sea ice is very dynamic. These are images from satellite that's passive microwave. The resolution is pretty poor. It's about 10 or so miles. So we're not seeing a lot of the fine scale details, but what we are seeing is motion. And I want to impress upon you that it's very dynamic. Because it's thin, it also retreats. Some of it simply melts away. That's normal. But the amount it's been melting has been increasing. So now at the minimum here in September, it's very low in the last decade or two compared to how it was historically, for most of the 20th century. The maximum is achieved here in March at the end. The next video is from another project, which was bridging a gap between two passive microwave satellites called Project Icebridge. So we flew aircraft in the Arctic to take more observations, but this was also an opportunity because these observed thickness, which was a real benefit because the normal passive microwave only sees coverage, the concentration of sea ice. And this really shows you all the different scenes of sea ice. So it started out being not very compact, with flows kind of separated by water, and then we're progressing now to these giant plates that are still able to move in the wind stress and ocean current stress. And that causes fractures that look like these long ridges and occasionally an opening. And it's winter, so the openings are refrozen and they still look like ice. I want to start with some stills before we get too far into this because it's hard to see what's going on in a video sometimes. This is a snapshot of what's a mosaic of visible images. And I hope you can recognize the difference between land and sea ice is a little hard to see in the winter scene like this, but I've labeled some of the Arctic villages along the coast, Kivalina, Shishmaref, and Point Hope. The ice itself is made up of flows and plates, and these range in size from 10 a foot or so to miles, so huge range. And they move with the ice motion. And they influence that motion, as you can imagine, smaller pieces move more freely. This is April, and it's just last year. So this is a normal start of the hunting season for these villages. And they're looking for openings in the ice. And you can see there are openings here next to Kivalina. That's great. So those are places where the marine mammals come to the surface and they can access them. But because the ice is moving, it's very hard to know when the ice is going to be open and whether it's safe and going to crush them. It's a very dangerous activity. And I've worked with this village of Kivalina for a number of years now by helping provide weather forecasts and discussions about wind conditions, as well as the sea ice conditions, to try to help with their concerns about safety. Sea ice thickness is also a major concern because it needs to be a platform to hold them. And if it's too thin, they can fall through. It's normal, though, that come summertime, there's no sea ice on the coastline in these regions. It's hard to believe because it was so wintry in early April, but by June and July, it's open, and it's actually a barrier island in both Shishmaref and Kivalina. So they have water on both sides, on the open ocean side and a lagoon side. And you can see this rock wall here. This is prevents surface ocean waves from crashing into the community. That's its intent anyway. It's a seawall. But for really big storms, they can still flood the village. And this is a major threat. And the storms are bigger during the winter and early and mid-autumn. So the sooner the ice refreezes in fall, the better to protect them from the potential of waves and storm surge. There's about 500 people who live here. And I also mentioned earlier that permafrost degradation is another problem that's causing coastal erosion. So this combination of waves and permafrost are kind of a deadly combination. And this is a picture taken from the Pacific Ocean side, looking at the village when the sea ice is present. So you can see it looks really kind of cozy. And the kind of message I wanted to make, though, here is that we've been calculating the amount of the duration of the open water season. And earlier in our satellite record, which begins in 1979, they would have about 100 days of open water. So it's normal, but then with climate change, that ice has been leaving. The ice out date, we call, is earlier and earlier, and then the ice freeze up date is later and later. So the duration has increased by about a month, so about 30 days more, starting from 100. So a really big increase. And as I mentioned, these waves are a serious problem for causing coastal erosion. Waves and sea ice have this really integral relationship, which sea ice attenuates waves. So waves can be generated locally by wind, but they can also propagate from long distances as swell. It attenuates both kinds. The thicker the ice, the higher the concentration, and the bigger the flows, the better it is at attenuating. And all of those things are changing as the ice is responding to the climate change that's happening globally. And it's such that when the ice is thinner and less compact, you really see more ocean surface waves as a threat. And in fact, some of these villages have lost their seawalls altogether, like Ukiyavik, which is on the North Slope. In 2018, a giant Arctic cyclone came by and just wiped out their seawalls. So it's still being rebuilt. In the meantime, they're using sandbags as a way to prevent coastal erosion, and this is protecting infrastructure in their village. This is a video, this is visible imagery as compared to that first video I showed, which was passive microwave. This is obscured by clouds. So you're seeing the clouds sometimes, I'm sorry, just day after day. Sometimes it's cloudy. In fact, it's often cloudy. But this was just this year. And there were a couple stretches that were low in cloud cover. And I like to show you this because I hope you get a sense of that real strong role between flows and ice motion and open water that is normal and occurring in April, where it's providing both the access to the sea that's desirable for reaching marine mammals, but it's also this threat because it permits ocean waves. Sometimes it's hard, though, to look at videos because there's so much going on. So I want to just show you just a series of scenes. These are from last year, starting in early April, and then about a month and a half later, it was the next clear day. It was really cloudy last year. And you can start to see just giant openings occurring near Point Hope and in Bering Strait. So those are regions that are starting to enter the open water season. And then a few weeks later, it's even bigger open water, but it can move. So some place that was once open can close. And so it's a very dynamic changeover from the ice to the open water season. That's normal and always a little hard to predict. But villagers have lots of experience and they're really good at predicting, but the climate change has really made their ability to predict much more difficult, as they don't have the same richness of experience that they had for centuries, right? And that's what it normally looks like in late June, and it's just a very thin bit of ice left that should disappear in a few days. So I've mentioned that the ice is involved in feedbacks that can amplify warming, and I want to kind of talk about that for a minute next. Normally in winter, it's very highly reflective and kind of more continuous and horizontal coverage. Once the melt season starts, water melts and pools on the sea ice and melt ponds, but the flows start to shrink in their lateral area and they become smaller, and then open water can appear between flows. So, all this open water and melt water that's captured starts to darken the sea ice surface, and it absorbs more sunlight, and that further increases the melt. So this is a normal feedback, but it comes to an equilibrium with a steady climate. But when we start to perturb the climate, it amplifies the climate change. So we'd expect that sea ice loss to be quite rapid when we have global warming, and then associated with, of course, the transition from ice to open water is a great deal of warming at the surface. So this should cause local warming and a higher rate of warming than we see globally. Uh, the Our system models that I've developed with my whole career are very successful at um, simulating these kinds of behaviors of the different types of sea ice, the flows, the motion, crashing, and deformation, fracturing. They have all that physics in them, as well as melt and growth. They do a pretty good job of replicating the observed sea ice extent that we see from the passive microwave satellite images. Starting in 1979, you can see the observations lie pretty close to the mean among all of the models, though the observations are actually declining at a faster rate. So they declined about 40% in the September, that's the end of summer, normal minimum time of the year. But if you just stitch September after September after September years, with 1 year apart, together, you see a record like this with a big decline. Um, the future of scenarios are projected with lots of different models. So we have this range with the uncertainty of models, as well as the scenarios shown. And a kind of interesting target people pay a lot of attention to is, when does it go ice free? And that occurs around 2065 for some of these kind of intermediate scenarios. Uh, Now, I'm also could show you volume and thickness of sea ice in projections, but I've decided to just mostly stick with observations for these records because they're so the change has been so large already, that I think that kind of speaks for itself. And I'm going to start with the lower panel here, which is thickness, and these are pure observations. We don't have one long-term record of sea ice thickness like we do for concentration in area. Um, because it's just harder to measure. And so it's a lot of different kinds, some stake measurements, some satellites, a bunch of different stuff. So it's noisier, and not as uniform number of different kinds of observations each year. But we can pretty clearly see when we combine all these different types that it's decreased a lot. It was about 3.5 meters, so it's like 17 feet or so in 1975, and now it's about 1.1, so 4 feet. It's a very big decline. Now, the product of thickness in area is, of course, volume. And there again, we don't have a great way of presenting that with pure observations because its thickness measurements are irregular in space and time. So instead, we bring it into a model in a observational model merge, and that is kind of take that in mind, that it's not pure observations, but it's our best estimate of volume, and that estimate is about 50% decline. These are efforts made by the University of Washington Polar Science Center, and really wonderful work they do there. Uh, so what this polar amplification looks like in space is, if we look at surface air temperature, for the last 60 years, just dramatically more warming has occurred in the Arctic. The ratio, the warmest values here is about 4 to 1 if we take the ratio of Arctic to global. So about a factor of 4 more warming in the Arctic. That's primarily due to the fact that there's sea ice retreating rapidly. Um, I'm really interested in making some predictions before we end here, and also, you know, talking about our opportunities or options for uh, reducing the threat. And this is a really nice way of presenting data that has been around for a little more than a decade here, that plots changes versus the cumulative CO2 emissions. And you've probably seen this global temperature anomaly versus cumulative CO2. It's a pretty famous picture because it gives us an opportunity to make a prediction. What we find is a pretty linear relationship. So the black dots are observations, and then there's simulations on top of that. And the cool thing is that they line up pretty much on a line. So it doesn't really matter how fast you emit, it's just a matter of time. If it takes so long to make so much emissions, you'll get there. And that gives you a predictable amount of temperature change for so many emissions. And turns out this works pretty well for sea ice too. And this was a paper just in 2016 that showed that the September sea ice area is well predicted by the cumulative CO2 emissions. And it's the slope of these lines that matters. So the observations have this kind of more or less linear slope. And there's a bunch of models shown which obviously have huge offsets, but they all have roughly the same slope. So they really support that the future projections are probably going to exhibit the same rough slope as what we see now. So this gives us a great way to kind of get a rule of thumb estimates for what we expect in the future. And what Nathan-Stowe said was we're currently at about 3 meters squared sea ice loss per metric ton of CO2 emitted. That's hard to kind of relate to. So let's think about it, what that means for us. In the US, our population emits about 15 metric tons per year. And so if we turn that into square feet, it's about 500 square feet per year per person that we're responsible for sea ice loss, which I think is kind of shockingly large. It basically says we can change the Arctic individually as a society as well. We can alter the sea ice future. I guess a kind of hopeful message from that is it's not too late. This isn't like showing a tipping point. It doesn't accelerate the loss. It's just a steady loss, a strong loss, but it's still something that we can estimate from current emissions. Another message from these figures is just what would it take to lose all of the sea ice? And usually we go with 1 million square kilometers as that value. So we come down here, it's about 1,000 gigatons more emissions from where we are today, which is similar to about 1 to 2 degrees of warming. We want to put that into perspective. Currently, humans are globally emitting about 38 gigatons of CO2 per year. So this would take about a quarter of a century. So that says we should expect sea ice loss sometime, like I showed earlier, about 2065. Now, we can also ask some kind of more local questions, like we looked at this kind of global scale or Arctic-wide scale, but I'm really interested in where the sea ice is disappearing fastest because humans live at the coast. And unfortunately, the ice is retreating from the coast first, and then eventually right into the central Arctic. So these Arctic-wide metrics kind of obscure the impacts on humans. And so we really should care about where it's disappearing first, and that is at the coast. Really, the impacts of sea ice loss are now. They're immediate. They're happening today. It's not about the future. Of course, it gets worse in the future, but it is somewhat irregular in space and time. So we can ask questions like, well, where is it worst, and where should we focus our efforts if we have that opportunity first? Can it be saved? Well, it can be saved by reducing emissions, but that's hard, and we haven't been terribly successful at doing that. One way we might have been was by making polar bears listed on the threatened species list, which I was very involved with. So I just want to briefly mention that this was a hope that it would drive the government to protect the bear, and the only way to protect bears, because their habitat is the sea ice, and the sea ice is being lost by greenhouse gas emissions, is to regulate emissions. But there was in spite of listing it, there was an extra sort of step that was made in 2008 to say we won't actually regulate because we can't directly relate habitat loss to emissions. But we've shown that's not true now. We actually absolutely can relate habitat loss and impacts on bears to emissions. And we did that in this paper in 2023. It hasn't changed the government's policies yet, but I hope one day it will. And I guess the bottom line is just to say that this would actually help humans everywhere, obviously. And I want to emphasize that's driven by a policy because of sea ice loss. But we'll wait and see if we can ever move the hand of the government. But the last thing I want to do is address, well, what can we do to adapt to the change that's occurring, since we're not seeing strong emissions regulations policies, especially in the US. And this was an idea put forward by no one here at UW, but people I know and have gotten to know, because at first I thought it was quite surprising and I really wanted to know if it made sense. Could we actually alter the sea ice, thickening it with flooding it with seawater? And they called this Arctic ice management. So a group has decided this is worthy of testing, and they're called Real Ice. And I consult with them, and I actually was in the Arctic with them in January when I was wearing 2 fleece coats. But earlier I had decided this was something I wanted to know if it really would help thicken the sea ice. So I took out an Earth system model and the physics that I had developed, and was able to alter it by adding this kind of concept of flooding it with sea water. And we just decided to go with flooding everywhere in the Arctic. And we decided to do that in October and November for 20 centimeters per year. And this is the response. And it turns out it's actually more thickening than 20 centimeters, which I had a suspicion would be the case, and it proved to be. So I want to talk about why that is, because it's kind of a hopeful option or opportunity to get an even bigger response than the effort you make to thicken it. But I also want to emphasize that I think this isn't not yet fair estimate, because I think we should actually be flooding in these coastal regions a little bit later, because normally the coast freezes up later than the central Arctic, and it really starts to freeze in earnest in about November. So you have to flood when there's ice there to flood. So we're working on that. But meanwhile, this group took up this idea and thought they wanted to test it with field programs. And so in 2025 and 2026, they've been flooding the sea ice. This is a photograph of their pump flooding, and it's in January, so there's low angle, beautiful light. But why does this work? Well, it's just briefly, the way sea ice grows is very interesting. It grows at the bottom, and that's because it conducts heat out of the ocean. The ocean is at the freezing point. So when it conducts heat out, molecules of water adhere to the bottom of the ice, and that changes latent heat and comes to energy balance. So you conduct that heat out, and you would grow more if it conducts more. So thinner ice grows faster, and so snow, though, is the mystery here. And when we add snow, because it's snowing and it accumulates on the surface, snow is a really good insulator, even better than ice itself. So snow acts like thick ice on top. It just really insulates, slows down the heat conduction. So counterintuitively, snow is not great for growing sea ice because it slows it down. But that's normal. It grows fast in the fall, and then as the snow accumulates, it slows down. And as it thickens, it slows down. That's normal. So when you attempt to thicken it, can you mess with this in an intentional way? Like, you don't want to actually inhibit the amount of natural sea ice growth at the bottom. But it turns out that it actually amplifies it, because if you turn the snow by flooding it with seawater into a slush, you've reduced the amount of that really good insulator that snow is and made it a mediocre insulator that ice is. So you've thickened it by making snow into snow ice. It's very similar to sea ice, but it's some slight differences in its structure. So it actually catches a little bit of air, which makes it a little bubbly, and that's good. Makes it more reflective. But because it has worse insulating capability, we've lost snow and replaced it with ice, it grows faster at the bottom. And so that amplifies the impact of the seawater pumping that we did to start by about a factor of 3. So it's a huge improvement. And we discovered that and published it. It was still just a concept. And this group has subsequently taken this idea to heart and now doing field experiments to test it. And essentially it's been very proven to succeed. Just to mention also that it's thicker, but a little bit bubbly will also postpone melt at the surface, which is another win. So I'm interested in using this to deploy right next to villages. Like, can we kind of make a augmented seawall by growing sea ice as a backup? So to postpone harm from coastal waves, to postpone melting of permafrost, to give villagers more platform to use for all the ways they use sea ice. And where should we do it? Can we actually anticipate, say in fall or early winter, where ice is going to be worse than normal? Because every year there's normal variability. And so it would be really cool if we could do this intentionally, where that you could predict that ice conditions are going to be poor, to adapt and modify the ice to make it thick again. And the question is that doable? And so we started with that as a kind of way to just say, well, can we deploy most efficiently by first predicting? And the truth is, yes, if your thickness is the goal, if you want to make your ice as thick as possible in June, then let's say January 1st, if you start with thicker than normal ice, it'll already be thicker than average in June. If you start with medium ice in January, it'll be medium. And if you start with low ice thickness in January, it'll be lower. And this is just without any flooding. So this is just the background or the climate behavior. But this means that if we knew ice was going to be low, we could note, in January 1st, a low ice year and adapt to it. So this field expedition, though, has only been just one village, is Cambridge Bay, Canada, as an experiment. It's a test site, but it is quite close to a village. And they've been flooding in these test sites. So they have controls and test sites. And the controls are shown here in orange and the test in purple. And snow starts to accumulate on the sea ice when it starts to grow here. This is a simulation in the straight line, but then the dots and X's are field measurements, showing models doing a fairly good job at the control compared to observations of thickness and snow. And then when we tested sites with flooding, that converts the snow into ice. So it immediately reduces the snow and thickens the ice. And then you get that extra factor of 2 or so, compared to 20 centimeters thicker here and now about 60 by the end of winter. So really, it's very effective in the field as well as in our simulations. So we can simulate quite closely to what we observed. And so the last slide is what this looks like from space and from drone images in these patches that were flooded. They're quite a bit more reflective and can be seen very clearly from drone images, as well as these are Landsat images on the right. So could see them from space, but had to wait until late May when there's a lot of snow, so it kind of uniformly covers everything. But the snow, once it was melted on the control, now you're seeing the little bit more bubbly and elevated ice on the flooded area, and they survive longer. So with that, I will summarize and tell you that what I talked about was that sea ice has this pretty dramatic influence on local as well as global climate, and humans and ecosystems really depend on it, both locally and globally. Sea ice has declined precipitously, and it's continued to decline in future projections. I think that's pretty clear and not too surprising. The further loss, though, can be directly related to human emissions. So we have a really good way of just by rule of thumb, kind of based on observations alone, estimate what kind of projections we think we will have and how reducing emissions today can help save the sea ice, which is by far the best way to save the sea ice, is by reducing emissions. We would love to use polar bears as a kind of mechanism to help enhance or make this policy more rapidly in effect, reducing emissions, especially in the US, where the Threatened Species Act demands it, but we're in this loophole situation right now that has delayed any action. But the last idea was just to test the idea of adapting. Can we actually locally thicken the ice where it can help communities most? And it looks like that's a doable thing. The engineering is another matter that is being addressed by others, but I didn't tell you about that. So I'll stop there and really happy to take questions. Thank you.
Thank you, Dr. Bitz. Really appreciate your insights today and the opportunity to learn a little bit more about how sea ice and global climate change interact and what we should all be paying attention to. Let's see, we've got some questions coming in. Just as a reminder for folks on any of the platforms that you are watching, please go ahead and drop any questions that you might have for Dr. Bitz into the chat or the comments, and we'll get to as many as we can. So Cece, I've got a few for you already, and yeah, let's get going. So let's see. Is there a scenario where other large climate tipping points, for example, the AMOC collapse, might cause sea ice expansion? You might have to define AMOC for folks.
AMOC is the Atlantic Meridional Overturning Circulation. And the AMOC normally, actually, I think I have a figure. I cut out some slides, and so I have some spare slides. It normally transfers heat to the north in the Atlantic, which is one of the reasons why the sea ice edge looks the way it does, right? It's furthest north next to Norway, furthest south in the Labrador Sea and next to Greenland. So it kind of is influenced strongly by this Gulf Stream and heat transport in the North Atlantic current. So the reason that sinks and turns into the cold branch that goes southward at depth is because the atmosphere is cold in the North Atlantic, and cooling makes the water dense and sinks. So, but it can be reduced if the atmosphere warms. So if the atmosphere is no longer as cold, then you don't make the dense water, so it doesn't sink. So we expect this circulation to decline. And that has some potential for actually a cooling effect in the North Atlantic, which ought to help sea ice preserve a little bit. And that can be seen in scenarios. So if we actually run simulations that are fully coupled so that the ocean is reacting to global warming and this whole process plays out with the thermohaline circulation weakening, the sea ice is actually a little bit less, retreats less than an ocean model that's no dynamics, that just is like a bathtub, a passive ocean. Yeah.
Excellent, thank you. Let's see, another question. We've seen a lot of glaciers respond exponentially faster to melt than models have shown due to compounding effects of mass loss. Is it possible that our models are too conservative? So for sea ice loss as well, that is?
Well, I think that that's pretty clear that they are, because we've basically seen this for decades now, that they're a little slower, and the only way they can get as fast as the observations is if they warm too much. So there's a spread of models, and some models have say higher cloud feedback, and that allows them to warm too fast, like we think, outside of what we can justify from observations. So yes, they're not sensitive enough. I think that's fair. And I think one of the reasons is because they haven't had flows. And well, also, it's just human nature. You want your model to be stable. It's not good when your model blows up. So we tend to choose conservatively when we do. But you can see here, sea ice can be super dark. That's sea ice everywhere in this picture. It's very dark when it's thin. It's really dark when it's got liquid water on top. So those are things we need to take into account, and we do, but probably a little bit cautiously. Also, the presence of flows, like, so it's going to animate, so it's going to drive us crazy. Maybe, yeah, this, yeah, anyway, not having a still flows. Flows, we have never modeled flows until like the last 2 years when I've been introducing them into Earth system models. So flows have a mechanism, changing lateral area that we've never had in Earth system models before. And that's a possible amplifier. I don't think it's going to be huge, but it doesn't have to be huge, right? We definitely get sea ice declining. We just need a little more. So definitely, I think we need to work on that.
Okay, let's see. With greater sea ice melt, are there more human marine mammal interactions? So polar bear encounters near coastal villages, for example.
Yeah, there's been a lot of news about that, right? Like polar bears have been, um, they're opportunists, so they'll definitely prefer seals. That's their favorite food because they're filled with blubber. Uh, but what else is whales, right? So they tend to intervene when there's a whale catch, and they definitely like the carcasses when they've been left behind. So leftover whale that the humans have given given up on. So yes, they're making a little bit of a living off of that, but there's many thousands of polar bears. There's not enough whale carcasses to substitute for seals. There's millions of seals, so it's not a long-term solution. But yes, they're
Gotcha.
more close to villages. I think that was the original question. Is like, and because they're taking advantage of the hunt, and that's dangerous for people.
Yeah. Does an ice-free Arctic in the future lead to sea level rise in other populated coastal areas globally? Or is just land ice melt that contributes to dangerous global sea level rise?
Yeah, I mean, it's a really good question, and I think it's indirect. So sea ice itself is embedded in the ocean, so it's already displaced the mass of water that it has. So when it melts, it fills the hole. It's like when you have a glass of water with ice in it, and when the ice melts, it doesn't overflow the glass. Same with sea ice, but it keeps the climate cold. So when the sea ice melts, Greenland warms much more, right? It's a huge effect on keeping the atmosphere around Greenland cold. So it's an indirect accelerant of land ice melt and sea
Mhm.
level rise associated with it. Yeah.
Okay, these two are two different questions, but they're related. Is there anything preventing the scaling up of the flooding devices to larger scale across all communities and ports? Are they solar paneled? And second part of that question is how much energy do you need to use to thicken the sea ice? What is the impact of that energy use on global warming?
I know it's definitely a concern, right? So the goal of Realize is to use hydrogen fuel cell technology. Obviously, that's not ready yet, but it could be a very clean energy. So the idea is not to pollute further and worsen the problem that you're trying to fix. That's clearly number one, right? But keep in mind that the sea water actually, because of hydrostatic balance, is actually not at the bottom of the sea ice. It's if you poke a hole in it, the seawater is only a tenth of the thickness of the ice below it. So poke a hole in the sea ice, seawater is right here, not here. So you only have to elevate that seawater 30 centimeters or something like that. It's not as bad as it sounds, maybe at first glance. But yes, the hope is to make autonomous pumps that can move to the location they're needed, melt through the ice, and then pump. But realistically, it still takes a lot of energy to do that. So they're going to have to come back to a mothership and get recharged. And that's all in the plans. But like I said, I'm not an engineer, so I didn't really want to get into it too much because it's a little bit out of my wheelhouse. Yeah.
Gotcha. Let's see. What are the implications of strong Bering Sea extratropical cyclones on sea ice coverage?
Oh, well, the cyclones are potentially harsh, bad for sea ice, right? Fracturing it, making the flows smaller. Cyclones bring in warm air in the warm sector. Uh, but on the whole, they also bring in air on the cold side too. So the effect of cyclones on the whole is probably close to neutral. um, like I said, there can be these secondary effects of fracturing the ice, but if it's winter, they'll heal, they'll weld back together, coagulate. So it depends on like time of year and all the other things, but for sure, if you get a cyclone right next to the coast where the cold sector is on land and the warm sector is on the ocean, it has a big impact. But that's a special circumstance.
Hmm. Let's see. Perhaps related, can you comment on the effect of Arctic warming on the Northern Hemisphere jet stream weakening?
Yes, this is one of my slides also that I cut out. um, so I'm happy you're asking. You've probably seen pictures like this is Hudson River frozen in February of 2015. And these kinds of cold air outbreaks, happen always in time, but maybe they're happening more often. It's been speculated that they're connected to Arctic sea ice loss and the strong polar amplification that we've seen in the last 50, 60 years. So question is, why would that be? Well, this pole to equator temperature gradient is what drives westerly winds at some level. And so if you weaken the pole to equator temperature gradient by warming faster at the pole, it should weaken the jet. And what's really been seen is mixed. It's hard, because there's so much internal variability in the atmosphere, hard to see a signal and hard to attribute a signal. So what's generally done is we have to resort to models where we can isolate things one at a time. And so these are atmospheric general circulation models with sea ice concentration imposed. So this is the sensitivity to a change in sea ice concentration alone. And definitely, just as you expect, it's going to warm. But the mixed response we see in sea level pressure should be a signal, an indication to us that the circulation of the atmosphere response is more complicated. If it's weaker, that's conducive with a slowing of the jet, but you can see there's some positives and negatives combined. So I did. I could talk longer about this, but again, just to get more questions, I think I'll just say that there's mixed evidence. It's not a dumb idea. It's a really interesting idea, and we definitely want to test this rigorously because it could be very serious for humans everywhere. But so far, it's hard to make the attribution definitively.
Gotcha.
Yeah.
Okay. Couple more for you. When seawater turns to ice, does it exclude the salt or exude the salt? Maybe both.
Yes, it it does expel, usually the nerdy term that we use. And it doesn't expel at all though. So that's kind of funky, right? Like it captures some of it. And however, I don't know, I don't have a good picture of this. It's too bad because it's super beautiful. It captures it in pockets because it turns out ice itself is pure water. And so it captures it in little pockets that are brine. So ice is a mix of droplets that are brine, really, really salty, very salty compared to seawater even. is all the salt got concentrated in this little drop of water. But it's a little bit spongy, especially as you get closer to the melting point. Those droplets are like irises; they get bigger, and it sort of melts from the inside out. There's at the surface, it often looks kind of rotten, and it's hard to tell the difference between melting ice and melting snow because of this effect. But if you look at it under a microscope, you can tell pretty fast. Yeah. So I couldn't tell you if that's snow or melting ice itself. The ice will look really rotten.
Mhm. All right, let's see. We're closing in here. Let's see. Are there any main emission sources that would make the most sense to target in reducing? And I guess relatedly, from where you sit, all of us who are sitting outside the Arctic, what can we do to maybe help on that effect?
Well, I'm definitely, telling you my opinion here, which is to do the things that are easiest first, and uh, you know, things that we have options, renewable options, efficiency options. When it takes so little effort to make a big impact, those are the things we should do immediately. And then obviously we really need to vote to make policy because it's a bigger problem than we can solve as individuals. But as a society, I think we have a big voice and we should use it with our ballot and get some policies that prioritize investment in green energy and in alternatives that are really um, big enough to solve this problem.
Excellent. Okay, one last late breaking, and then I've got a wrap up question. Would we expect that Antarctica and the sea ice near it would have a similar response?
Yes and no. Do you want another talk? um, yeah, so Antarctica had for a while not been retreating, and that really puzzles the sea ice scientists of the world, climate scientists as well. But it has turned around and now it's really rapidly decreasing. So really all the same feedbacks. This kind of feedback should happen in the Antarctic. But the Antarctic is different in so many ways. Like it normally never melts at the surface in a large area. It's too cold. The Southern Ocean is much colder than you would expect by latitude. So it actually melts and grows from the bottom, which is weird and different. So it doesn't make these melt ponds, but there's always a bit more heat kind of coming up from the ocean because that's where the thermohaline circulation pops up, and it's just enough heat to mess with the sea ice. So it's different in some ways, and it's very very integrated with the you know ocean. I think the Arctic is too, but it's sort of more so in the Antarctic because the Southern Ocean has no boundaries. It's like this giant current that has circles the whole continent. It's very high speed compared to the Arctic, and it's just very dynamic environment. So there's lots of reasons why it's a little different, and we have good theories, but not maybe too many theories, right? We haven't really honed in on the right answer, I think, or one certain answer.
The bottom line is it's complex.
Yeah.
Okay, well, I've got one question that I'm just curious about. Give us a little glimpse into what a day in the life of being an Arctic researcher is on the ground up there. I mean, you did show us the one photo of you all bundled up, but what's it like just to go about daily life there and prepare for those trips and visit such an environment? Give us a little glimpse of that. That's something most of us never get to see.
Sure, thanks. These have been really wonderful questions. Thank you so much. Well, we could, in that kind of dress, be outside for 2 3 hours comfortably. It was minus 35 Celsius, which is pretty close to minus 35 Fahrenheit. It was quite cold, and it can get much colder. It can even get down to minus 60 Fahrenheit. So quite cold, and when I was there, it was just kind of normal cold. um, so we worked on the ice for a few hours at a time. And then we would warm up in a little tent that we had that we left overnight. So we would take snowmobiles from town, which was about 10, 15 minute snowmobile ride, and then have that tent as a safety backup. So we didn't say it's been long days. This was actually January. It's totally light out, which totally surprised me. Like I thought it would be a very dark experience, but it's amazing how much your eye can see in dim light. So the light wasn't the problem, but it didn't warm you. Like you could face the sun, and it was just like, wait a minute, there's nothing warming me here.
Right.
Um, yeah, very fascinating experience.
Very cool. Excellent. Well, I think that about does it for us. Thanks, Dr. Bitz, for joining us and sharing your insights today. Really appreciate it. Great way to kick off Pacific Northwest Climate Week. And thank you, everybody, for tuning in and hearing what Dr. Bitz had to say about the Arctic. We appreciate your time and attention. For those of you that are interested in all of the research that's coming out of the College of the Environment, we invite you to visit our website and subscribe to our newsletter. We're constantly shining a light not only on what's happening in our polar regions, but in all of our oceans and across all of our continents, and even what's happening out in space. Pretty big place, lots of fascinating research happening here at the University of Washington College of the Environment, of which Dr. Bitz is a big part of. So thank you all so much. And with that, have a great day.